In 1950, at lunch in Los Alamos, Enrico Fermi asked a passing question about aliens and then went back to work. In 1975, an astronomer named Michael Hart turned that passing question into a formal argument for why we are probably alone in the galaxy. In 2018, three researchers at Oxford published a paper showing that Hart's argument does not survive contact with the actual mathematics. Almost no one has heard of the 2018 paper. Videos about the Fermi paradox continue to be made as if the question is unresolved. Books continue to be written about the Great Silence as if it demands explanation. The paper sits in the literature, cited and respected, and the popular discussion goes on almost exactly as it did before. This video is about that gap between what the field now knows and what the popular discussion is still saying. It is about how a question can be technically dissolved and remain culturally alive. And it is about what actually remains of the Fermi paradox when the assumptions it depends on are examined in the light of the last decade of research. The story begins with the lunch, and with a specific misattribution that has become part of the folklore of science. Fermi did ask a question at Los Alamos. The people who were there remembered it as something like, "Where is everybody?" He was responding to a conversation about UFO sightings. He did some quick calculations on a napkin. Then lunch ended. He did not publish. He did not return to the question. He did not consider it a paradox. The Fermi paradox, as we now use the term, was constructed 25 years later by Michael Hart in a paper called An Explanation for the Absence of Extraterrestrials on Earth. Hart argued that if intelligent civilizations exist, they should have colonized the galaxy by now. The absence of visible colonization was evidence, he said, that we are probably alone. Frank Tipler sharpened this argument in 1980, and the combined framing is what most people mean when they talk about the Fermi paradox today. The name is a small historical inaccuracy. The argument underneath it is not. Because when the assumptions Hart and Tipler built into it are examined carefully, the paradox does not survive them. There are three assumptions. I will take them in order and I will follow a specific hypothetical civilization through each one to see what remains. Call the civilization Kepler 442 after a real exoplanet in the habitable zone of a real star. Suppose Kepler 442 arose 10,000 years before us, a blink of an eye on cosmic timescales, and developed technology, industry, and the capacity for interstellar travel. The first assumption is that expansion is what intelligence does. Hart's argument assumes that Kepler 442, having reached interstellar capability, would use it. It would expand, colonize, and continue until the galaxy was filled. This is presented as obvious. It is not. It is a specific claim about behavior, and we have no good evidence for it. In the only case we can observe, our own, expansion appears to be a phase, not a destiny. Civilizations expand and then they stop. Much of our most advanced development now is not outward but inward. Smaller systems, denser computation, more capability in less space. Our frontier is moving into substrates rather than across distances. If Kepler 442 followed a similar trajectory, they may have reached the stars and simply chosen not to go, not because they failed. Because expansion stopped being the interesting thing to do. None of this proves that civilizations do not expand. It means expansion is a hypothesis, not a law, and the paradox depends on treating it as a law. The second assumption is about time. This is where the paradox stops being intuitive and starts being mathematical. The Fermi paradox is usually framed as a question about the present. Where are they now? Why don't we see them now? But now has almost no meaning at galactic scale. Kepler 442 is about 1,200 light years away. When we observe it, we see it as it was in the year 800 before the Vikings reached North America. If they transmit a signal today, we will not receive it for 1,200 years. If we transmit today, they will not receive it until the year 3,225. There is no shared present, only overlapping pasts and futures. Now consider how long a civilization is detectable. Suppose Kepler 442 broadcasts for 2,000 years, longer than our entire recorded history, and then stops. If they stopped 6,000 years ago, their signals passed Earth before we had radios. If they started recently, their signals have not arrived yet. For us to detect them at all, the timing has to line up almost exactly. Two civilizations separated by 1,000 light years might exist simultaneously for 100,000 years and never once occupy the specific overlap where either could see the other. This is where Sandberg, Drexler, and Ord did their most important work in the 2018 paper. The Drake equation is the standard framework for estimating the number of communicating civilizations in the galaxy. It multiplies together the fraction of stars with planets, the fraction of planets that develop life, the fraction of life that becomes intelligent, and several other terms. If you plug in single best guesses for each, you get a clean-looking answer. That is how the equation is almost always presented in popular treatments. But the inputs are not clean. Several of them span many orders of magnitude of genuine uncertainty. The fraction of habitable planets on which life arises, for example, could plausibly be anywhere between 1 in 10 and 1 in a trillion trillion. When you use single best guesses in place of that uncertainty, you are collapsing it into a specific number, and the collapse produces a specific and misleading result. It produces the illusion of confidence that the true answer sits near your guess. Sandberg and colleagues redid the calculation using probability distributions instead of single guesses, representing the actual uncertainty in each term rather than pretending it away. They propagated the uncertainty through the equation the way a physicist would propagate error bars through a real measurement. The result does not narrow. It explodes. And when you do that, the paradox doesn't weaken. It disappears. The probability that we are alone in the observable universe is not negligible. It is substantial, on the order of 1 in 3 to 2 in 3, depending on how you set the distributions. This does not mean we are alone. It means that being alone is entirely consistent with the data. There is no contradiction, no tension that requires resolution. The great silence is exactly what our actual uncertainty predicts. A related result from Adam Frank and Woody Sullivan in 2016 approaches the problem from a different angle and reaches a complementary conclusion. The popular Fermi paradox asks whether other civilizations exist right now. Frank and Sullivan pointed out that this is not the most answerable version of the question. The more answerable version is whether other civilizations have ever existed anywhere in the observable universe. When you separate those two questions, something specific happens. The threshold for us to be the only technological civilization that has ever existed turns out to be extraordinarily low. The probability of any civilization arising on any habitable planet would have to be smaller than 1 in 10 billion trillion. The question of whether we are alone in space and the question of whether we are alone in time are not the same question. The popular Fermi paradox conflates them. The technical literature does not. Once you separate them, the paradox splits into two much more manageable pieces, neither of which requires the extreme explanations: the great filter, the zoo hypothesis, the dark forest, that the unified paradox has been used to justify. The third assumption is the most fundamental. It is about what a civilization is. Return to Kepler 442. When we imagine them, we imagine something like ourselves, biological beings on a planet, building structures, transmitting signals into space in patterns we could recognize. This is a picture. It is not a definition. there is no reason to think it is correct. A civilization 10,000 years ahead of ours might have transitioned to computational substrates that use energy at a small fraction of the level we currently associate with technological activity. It might have distributed itself across systems in ways that are not spatially centralized in the way a planet-bound species is. It might have solved its fundamental problems in ways that give it no reason to broadcast, no reason to expand, and no reason to make itself visible. The paradox depends on the assumption that we know what we are looking for, but what we are looking for is a version of ourselves, biological, planetary, radio-loud, expansion-oriented, projected onto the sky. Kepler 442 does not have to be radically different from us for us to fail to see them. They only have to look like whatever we become in the next 500 years. And we do not yet know what that is. If our own trajectory is any guide, it is not more radio broadcasts and more colonization. It is smaller signatures, denser computation, and a technological footprint that shrinks even as capability grows. A civilization following that trajectory would be nearly invisible to the specific instruments we are pointing at the sky, not hidden, just outside the search space we constructed when we assumed they would look like us. The three assumptions: that intelligence expands, that now is a coherent question, that civilizations look like ours, are the load-bearing structure of the Fermi paradox. Remove any one of them and the paradox weakens. Remove all three and there is nothing left to explain. This is what the 2018 paper actually showed. Not that aliens do not exist, not that we have found them. Something quieter and more useful, that the silence we observe is exactly what our actual uncertainty predicts, and that the elaborate frameworks built to explain the silence, the filters, the zoos, the forests, were built to answer a question that turns out not to be there. What is left, when the paradox dissolves, is not nothing. It is a different set of questions, better ones. Not, why is the galaxy silent? The galaxy is not silent in any way that requires explanation. Our instruments cover a narrow band of possible signals across a narrow band of the sky, across a narrow window of time. The silence we hear is the silence of a very small ear pressed against a very large wall. Not, where is everybody? Everybody, if they exist, is separated from us by distances that make simultaneity meaningless and by trajectories that may make visibility optional. Not, what is the great filter? There may be no filter. There may only be uncertainty large enough to contain every outcome, including ours. The questions that remain are different. What would a civilization on a different trajectory than ours actually look like from here? What is the specific probability distribution across each Drake equation term? And how do we tighten it? What have we been assuming about intelligence and expansion and visibility that we have never examined? What does our expectation of noise tell us about ourselves? That last question is the one the paradox was always secretly about. The Fermi paradox was never really a question about aliens. It was a question about us, projected onto the sky. It assumed that intelligence must expand because we assumed we would. It assumed that civilizations must broadcast because we did. It assumed that a universe with other minds in it would look loud because we imagined ourselves getting louder forever. The universe does not look loud. The mathematics of our own uncertainty says it should not. And the picture of the future that the paradox was built on, the endlessly expanding, endlessly broadcasting, endlessly visible civilization, is starting to look less like a prediction about what intelligence does, and more like a self-portrait of one specific species at one specific moment in its development, drawn before it had the tools to see itself clearly. Fermi asked a question at lunch and moved on. He did not think he had discovered a paradox. He was right. What Hart and Tipler constructed 25 years later was not a discovery. It was a hypothesis, and the hypothesis has not survived the last decade of work. The Great Silence is not a mystery to be solved. It is the sound of a picture of the future failing to match the universe. And the question that remains, quieter than the paradox and much more interesting, is what we do now that the picture has changed.